About ready?
Sure.
Okay, so we're going to get started. Our next speaker is Justin McCarty from NMotion. He's going to talk about continuous integration system for NASA software with NMotion. He's from NASA IB&B.
All right. As I said, my name is Justin McCarty. I'm a member of the ITC Team, which is the Independent Test Capability Team out in Fairmont, West Virginia. And I'm going to give a brief overview of what we call NMotion, which is our continuous integration system for NASA software. So what I'm going to go over is, so it's kind of loud, a little bit of background on who we are, very high level. Another colleague of mine is giving a better presentation on Thursday about more in depth what we do. We'll go over the motivation of why we decided to go with this type of solution, some implementation information, very high level, some of the challenges we've had, what we would like to do going forward, and some conclusions. So just a little bit of background. What we do at the ITC team is we develop simulators for systems, so we're not directly related to any one project across NASA. So we like to think of ourselves as experts in simulators and software integration, not necessarily the flight software. One of the things we did is we developed what we call the NOS architecture. It's a software-only solution for implementing protocols such as FIT53, SpaceWire, so on and so forth, that we use in our simulations. We operate system test automation, which is mostly what I'm talking about today. And some of our typical users of our architecture are V&V engineers, project developers, and operators and testers. So this is just a quick list of some of the projects we've supported and are currently supporting. This is not all of them, but we've dealt with Juno, the AFSS Meta-Wallops, the Global Precipitation Measurement Satellite, GPM, out of Goddard. We're working with the Deep Space Climate Observer, DSCOVR, and JBST currently, which is our big flagship. So like I said, we work across a lot of different missions, so we kind of see what a lot of people are different doing. So some of the motivations for this type of system. One is simulation verification. We develop simulators. We would like to make sure that our simulators are doing what we say they are doing and that they operate correctly. We've noticed across a lot of systems and how the tests are run and operated that these test processes are very repetitive. Run the script, take the output, parse the output, give result. So on and so forth, rinse and repeat. And also, we believe better testing means better software. The more often we test, the longer we test, the better we test, the more confident we are in the software we are doing. This is an example of some of the test complexity that we've dealt with running some of our own systems. It's talking about a test script from the James Webb Space Telescope. It verifies all of the testable requirements for a component within James Webb. It's a very complex test, over 8,000 lines. As you can see here, 282 commands, over 36 of which are unique. There are 106 number of times the application is suspended during the process. There are 382 waits, not including any looping that may occur. And this accounts for over 3 hours of wait time alone, without counting any processing. In reality, the test log shows that this type of test takes over 8 hours of human testing. And that's assuming it works on the first shot, which nothing ever does. So for each failure, each time we rerun, that's another 8 hours, 6 hours, 3 hours, however it is. And this is just one test. And as the test is developed currently, the test builds on itself. So if you fail halfway through, you may not be able to recover and continue testing. You may have to start at the beginning and keep going. So now I'm going to go over some of the high-level implementation details. I do want to point out that this is kind of prototype software, so this is by no means complete. So keep that in mind. So what we did for implementation is we used the James Webb Simulation and Test Environment prototype, which is GIST, which we developed in-house. We're dealing with both the ISIM side and the spacecraft side, for any of those familiar with James Webb. So we have to take into account everything with it. We've developed most of the parts with C and C++ and some Java for test control. I'm not very doing presentation, sorry. We have the automated unit level testing for not only our model for the flight software that is run, that are delivered to us, we run those tests, we run our own unit level tests, and we run system level tests. For implementation, we use a three-phase testing process, first being system adaptation. So we adapt what we're given to be able to run within this kind of automated environment. We do test execution, and then we do the results analysis that comes out in the end. We favor cloud-based deployments for our own processing because we deal with a lot of different centers. Even some of our own team members are not co-located, so we have to be able to run it within the cloud. And what we currently have requires no user code, no end user code be written. So we're not requiring any new language to be learned, any new long list of steps you have to follow. We just give a list of tests we run. So here's a very high-level overview of what the architecture looks like. As you see on at the very top in the dark gray boxes, we take a list of user test files that need to be run. They're given to the automated test conductor. This is the guy that kind of is the brains of the operation, so to say. He's able to talk to our NOS middleware for interaction for protocol information. And then it also talks to these separate command processors that we operate with. And these are the guys that integrate with, say, the operational ground system. We use instruction set simulators to run the actual flight software. There can be one or more of these, and I don't think we've run in a scenario where we've ever had one. So we've run multiple one, and it does make sure everything is running, is healthy, is good, data is processing, and then in the end, we generate the test log. We give the test logs back to the end user so they can see what happened in every process, and then the results validation that we have parsed out of these logs. This is a example of a command processor. We have the conductor I/O control at the top. This primarily handles, right now we talk via sockets, so this handles the network communication, high-level protocol breaking down. And then there's the processor, its logic itself to know which commands go to which application, what it should be doing, reporting health and status. And then we have several API blocks. So we don't necessarily have to have, if you run 5 applications on one machine, 5 of these processors. We use a plugin architecture so we can interact with API 1, API 2, API 3, so on and so forth. And they can be dynamically added and loaded. Here's an example of some very basic data flow that occurs. So the user would pass the test to run into the test conductor. Some commanding such as start commands, make sure the system is started in order, the correct ones are running. And then from there, the test conductor pretty much takes control. He sends any setup instructions, initialization to each of the processors in turn. So if there are examples of order concerns, say the middleware has to be up prior, then the ground stations can come up, so on and so forth. It'll make sure ordering is taken care of. If no ordering is required, then it will bring them up in parallel as best it can. Once that's up, the application will the command processor will start relaying status information back to the conductor. In most cases, this is just, hey, my application is still running, it hasn't exited prematurely, everything is fine. If more control is needed, then it will come back. That's kind of at the API level where we interact with. And then after some time later, the command processors will actually transfer the application logs back to the conductor for the processing, for parsing. If they need to be zipped up before they're returned, if they're very large. And then at the end, those test results and the test logs are given back to the user. So like I said, as you can see, there's really not a lot of user interaction needs to be in here. This is designed to be very automated, very easy to use. So about those phases I was talking about, we have first is the system adaptation phase. One of the biggest parts of this is pre-processing the existing tests we are given. For the example of JFC, like that one I had shown. What we do is we remove any deterrents that are simply waiting for user acknowledgement, say, press go when you're ready. That's not needed. Things like that. We convert what JFC has raw commands, which take a separate control flow and require the user to acknowledge that, yes, I want to send this as a safety precaution. We convert those to actual commands so that they are no longer delayed. We also ensure that all the files that we need are found. We have been delivered some tests where we weren't given everything, and the pre-processing was able to find that ahead of time, so we didn't try and run without all the files. And we also ensure that the test results can be processed. Some of the tests we have run, this hasn't been possible. Either if they fail, they just exit in a I'm done, and there's no printout, there's no failed status, there's no failed message, no counters. Some have been very nice about failing, hey, I failed, 5 failed, 4 failed, everything else passed. Great, so we want to make sure that what we're running, we don't mark something as passed when it really didn't. We also want to ensure that all the components involved with the test, that we can interact with them remotely. This is unfortunately not always the case. Sometimes interaction can just be stopping a process to which we don't need to interact with the application directly. We can just launch at the OS level. Sometimes not. And then we want to know if we have to be able to do command injection, start this process, start this configuration, so on and so forth. We have to really take a look at a lot of the applications. Some applications we've seen have claimed that they can be run remotely, and that hasn't entirely been true. They've gotten you about 90% of the way, but not always. So we kind of like to watch what goes on and run these tests. Obviously, these are self-ones to make sure this will go as we think it will. Execution and processing is actually really simple at the generic level. I do like to point out that the test scripts that we are running are the exact same ones that system developers and operators are running, with that minor exception of we remove the deterrents. So those are the only modifications that we are making to the scripts. One thing we do is we make sure we reset the system, the entire environment between each test run, so that we make sure that there are no leftover file handlers left open. So maybe the ground station got put in some corrupted state. Anything like this, we want to make sure we are clean each time. So that, like I said, reset. The test conductor ensures the applications are brought up in the order. I mentioned that before. Like I said, we've had scenarios where the middleware has to be up prior, or the ground station has to be up before the flight software comes up, or vice versa. One of those scenarios. The user provides us a list. We can either run one at a time, or we can take batch execution. Pretty much for the James Webb, what we've done is just said, give us a list of known what they call proc files that we're going to run for our test files. We go find them, make sure they're run, and that they're there. Again, application health is monitored because that's been a big thing. We've had processes die in the middle of testing, and then we had no idea until the end. We had about 12 hours testing in, and we found out one of the simulations that we ourselves had actually developed had died midway, and we wasn't reported in our first attempt. So all those tests were invalid. And then finally, like I said before, we parse those test logs for any failures that have occurred. Pretty easy parsing. So some of the challenges we've had implementing this kind of system, obviously these are not, here's just a few of them. They're kind of the biggest high-level ones. One of the really biggest ones has been a culture. A lot of the tests that we've run into were not developed with automation in mind, because that's not how they're usually run. They're usually run manually with human in the loop. And so they are designed that way. Acknowledge you're ready to run. Proceed the next step. Refer to document X to see what you have to do next. All the steps aren't there. And we also run to a lot of developers and testers write their tests with the mindset of, this runs in my lab, under my configuration, under my known instances. So when we take those systems and we bring them into our labs or our cloud-based environments, obviously they're not going to necessarily be the same. And sometimes these problems come down to, we know there is this machine named JP8934, whatever it may be, and that's not documented anywhere until we go through the scripts and goes, oh God, why can't it run? Well, that machine's not there. So either we emulate it or we change it, whichever the best way. Like I said, we've looked at a lot of missions, and we haven't seen a lot of reuse of simulation tools. Even today we've heard a lot about, flight software components like CFTP, CFE. Those are reused, but the simulation tools are not, and a lot of them do the same thing. So every time we look at a new mission, we have to relearn new tools, new pieces, and they're really doing the same thing. But just either they don't know don't know they're out there, or they decide to develop their own, Who knows? And again, some of the project infrastructure for running these tools are not developed with automation in mind because human loop is generally almost always there. So they expect a human to be there to go click start, run process, do this. Not always an option for us. So going forward, we have a lot of ideas for this architecture. It's proven very helpful for our own running of our simulation environment, and we really want to grow it towards other missions. So one thing we definitely want to do is we want to integrate the system we've developed into our automated build server for our own tools. So then not only when we develop simulation components or hardware models, we would like, when the nightly unit tests and system tests are run, then why don't we do the regression tests for the entire, for that simulation. So in JWST's case, we run through all their tests, operate with Discover, run through their tests, so that we can have a measure of how well we're doing with our simulations and how they're improving, how they're failing. We would like to allow users to inject faults to test off-nominal scenarios with these automated tests. I had mentioned that NOS middleware. One thing that a capability that allows us to do is we can inject commands and faults in the communication process. So typically, say from a ground station, there may not be a way for you to say, hey, turn off all transactions to this RT, see how the system operates. In some situations, we have seen tools that allow you to do that. Some we have not. Our system allows you to do that, so we would like to be able to put off-nominal scenarios in there. The code obviously needs to be refined. Like I said, it's a prototype going on right now, so it's not polished by any means, which kind of is a proof of concept to see how we can run. We would like to take the code we have developed, though, and integrate it with other simulators that we've done. I mentioned Discover. We have GoSim for GPM. On some of our future projects we like to work with, we want to make sure we can just plug our tools into this framework and let it run. We want to support the scripting of the environment setup. Currently, right now, we know, because we're only running with JWST, we know the order processes for tools that have to come up. We know what can be done in parallel, what has to be done in order. We want to allow a user to provide that information for us. So maybe one of their tests is making sure if this isn't up, our environment's not saying, fail the test. Or it could be, that way we don't have, also, so we don't have to know every little detail about the system. That'd be kind of nice. And we would like to be integrated earlier in the development process. For most of our simulation processes, we come in towards the testing side, towards the end. So development of project simulators that we don't do have already been done. The tools have already been developed. So going back to the developer and saying, hey, can we do this remotely? They may tell us, why are you talking to us? Please do what we asked you to do. So the earlier we get in there, the more impact we can have, and the more we can kind of help shape to make sure that the tools can all work to everyone's best advantage, to be quite honest. So conclusions, it's kind of a really short presentation, sorry. What this kind of architecture allows us to do, we enable a higher level of automated system testing that we've currently seen. I know Laddie mentioned they do some testing. That was the first we had seen of that. So I do want to talk to you, actually. But it does enable higher levels testing, we believe. Again, it provides more testing. If we integrate these with automated build servers, we don't have to wait till there is someone at the hardware. Maybe there's only 2 hardware strings, you have to schedule time. With software-only environments, we can say every night, run every test that we have. Maybe running all these tests takes a week. Fine, whatever. Run just continuously as there's code check-ins, big check-ins. Provide better feedback to individuals of what's going on. Again, we plan to expand other systems. The plugin-based operation is there mostly. As part of the code refinement, we want to make sure other users can develop plugins themselves easily for their systems, so they know kind of what we're looking for and what they're looking for. Makes sense? People who benefit from what we do, testers benefit, simulation developers, we believe, benefit, and the project developers themselves benefit. Because everyone gets better code. Better testing, better code. And then if tools and tests are developed with automation in mind, new project adaptations for simulators and transitions will be much faster. We'll already have a base set of tools to run with, a base set of knowledge, and we can just go faster and faster and provide better results for the project as we go forward. So that's kind of all I have. Here's some basic contact information. Justin Morris is actually our government lead, so you might want to talk to him. But that's about all I got. So.
Are there questions?
I think earlier on you said you needed to have a model provided. Is that a hardware model, like an engineering verification model?
Yes. A
simulator is what you said.
Yeah, the simulators. Well, what we test with, we use the instruction set simulator I had mentioned before. We work with Symix and QEMU to develop those hardware models if they're not provided by the project. In the example of MPCV, they were nice enough to provide us with their models. Simulators could also be in the form of GDS, the Goddard Dynamics Simulator.
Is that a software? I'm not familiar with that. Is that software or is that hardware?
GDS?
Yeah.
GDS is a software application meant to communicate with the real hardware. We've kind of adapted that to talk to our virtualized hardware.
I see. Okay, do you have any consideration for tests like you fly? Or is the code so heavily instrumented you really can't do it that way?
Oh, no. Dustin will talk more about this in his presentation, but we run the actual flight binaries. We don't instrument it. We don't make any modifications to it. So we're running exactly whatever the build we're given from the project is.
So do you have a capability to stub out processes that may not be delivered yet so you can do early testing?
Like instruments and stuff like that?
Well, something if there are multiple CSCIs that get delivered, yet you don't have the full suite, that may preclude you normally from doing testing unless you can stub out the missing ones to give just kind of knee-jerk response.
Honestly, at the moment, I really can't give you a good answer for that question. What we've been at is we already have formalized builds that have been delivered to IV and V. Mm-hmm. So the program's are already there. Wow, I just completely blanked on that. So we already have kind of complete builds, either that are stubbed from the project or.
Okay, last question is, seems like this have a lot of use for regression testing. Mm-hmm. You can just run it overnight and get the results in the morning and see how. Yeah,
that's actually one of the things we wanted. We were developing our hardware models for JVST. The first release we did of our simulator, I think we had a dedicated month of just testing and rewriting the same scripts over. So we kind of wanted to cut that time down from our own selfish needs and it really just make a better product. So yeah, we wanted this process so we can do regression over and over and over and over again.
Thank you.
Other questions?
I don't think he likes you.
In an optimal world, where would you like to start working with a project in their development process?
I would say probably in an optimal world prior to the code being laid down.
What are the earliest artifacts you would be interested in IV&Ving?
From the IV&V project, I can't honestly answer that the best. I'm not an analyst. For our point of view for developing our simulators, we rely heavily on the ICDs, very heavily. I think I've gone through the ICDs probably about a dozen times in like a week trying to find information. So that's one of the big artifacts we rely on. And actually also test documentation for how they plan on doing tests has also been extremely helpful in finding what kind of environment we really need to have for the existing tests to run. Because we don't want to recreate the wheel and provide, and redo the work that's already there if we don't have to. Yep.
I think I might have missed something here. Did you say that if I were to come to you and I wanted you to test my flight software, do I give you the scripts that I want you to run, or do you develop those based on my requirements?
The way the ITC team has operated is we run the scripts that have been delivered by the project. However, IV&V analysts also go through the process of developing their own scripts to test validation. We work very closely with the IV&V teams for each project.
Okay,
So it's kind of a combination.
Okay, because for you to develop your own scripts to test my software would be invaluable. Okay.
Yeah, the IV&V teams do that quite a lot.
Okay, thank you.
I gotta say, I'm really shocked and appalled that you're wasting the taxpayers' money by allowing your subcontractors to even consider having human-in-the-loop testing occur. And I've got a very strong sense of deja vu. We could talk later about that. But is this a hole in your flow down to the contractors to say, thou shalt deliver verification tests or deliver test sets that support complete end-to-end automation of tests?
Well, as a contractor, I would actually kind of really love that, to be quite honest, because we like a lot of direction. And in a perfect world, yes, the government can do that and say, hey, you shall do it this way, and we shall run, and we can run, and that would actually make me very happy.